Hey everybody, Trey here. Welcome back to another episode in this Skew-T and Hodographs series. It's been a while, but we're back. In the previous video, we discussed, kind of wrapped up our discussion of hodographs by looking at a bunch of common hodographs you might see when making a severe weather forecast. And today we're going to move on from that in this video. We're going to look at the SPC sounding and the model sounding. And we're going to go through every single box, every single parameter on this sounding. And I'm going to tell you which ones that I like to focus on when forecasting severe weather, which ones I think are kind of more important. And we're also going to take a look at some ones that I don't think are as important, but nonetheless, we're going to give you we're going to explain every single one of these boxes, every single one of these parameters on these soundings so you can know what you're looking at when you are making a forecast. So we're going to split this up into a few different videos here. Today we're going to talk about the top half of the diagram here, the Skew-T and the hodograph here, and the boxes kind of around that. And then in subsequent videos, we're going to go through all these different parameters and boxes down here on the bottom of the hodograph. So this might take a few videos to complete here, but we're going to get you acclimated with what all of these variables mean. And one more thing here, we're going to bounce between the SPC sounding here and the model sounding here. Now they're plotted in pretty much exactly the same way. They use a program called SharpPy, and it's basically just a code that allows it to ingest the raw data and plot out these soundings and all these parameters here in this kind of nice, neat fashion. They're basically exactly the same, but the model soundings have a couple of different things about them compared to the SPC sounding. So even though they're almost exactly the same, we're going to highlight the small differences that do exist between the model soundings and the SPC soundings as well. So without further ado, let's get started here. We're going to start on the left side of the diagram here, which is, of course, the Skew-T. And we're going to start at the very top right. So at the very, very right corner, we have the station identifier, which in this case is LZK, or Little Rock. And then we have our date and time. So the date is given in a little bit of a unique format. It goes year, then month, then day. And then, of course, we have our Zulu or UTC time here. So this sounding was given on December 11th, 2021 at 0Z, or 6 p.m. Central Standard Time on December 10th. But again, it goes year, then month, then day for the date. So then we have our Skew-T. So on the left-hand side, of course, we have our pressure contours here, our pressure values. On the bottom here, we have our temperatures that correspond with each isotherm. I'm not going to go through every single grid line here. We did that in the very first video of the series. But the isotherms, of course, are along the bottom here, the temperature values. And then we have our distance above ground level with the surface parcel here. And the surface parcel has some extra information. It has the distance above mean sea level here, which in this case is 173 meters. And then it goes up every few kilometers here in the atmosphere to make it a little bit easier to pick out distances above the ground. So, of course, then we have our Skew-T. We have our green plot here, which is the dew point profile. The red plot is the temperature profile. And then we have our parcel trace here, which is this dark brown dashed line. So I'll trace that out for you here so you can see it a little bit better. So that is going to be our parcel trace. Now, previously in the series, we've mentioned that there are a few different parcel traces you can actually do. And they're given down here in this first box. And we're going to talk about that in the next video. But I want you to know that this dark brown trace that you can most visibly see is using the most unstable parcel. So we're going to talk in detail about this in the next video when we go over these instability metrics down here. But know that this is using the most unstable parcel. So when we did in video 2, we constructed our own hodograph. We started at the surface parcel, and we drew the parcel trace that way. Well, of course, that is the surface-based parcel trace. So, again, the SPC plots the most unstable parcel trace for its soundings. Now, you can see a little bit of a lighter brown one that kind of separates from the most unstable one here. I believe this is the mixed layer parcel trace. I'm not 100% sure. Couldn't find any documentation on that, but it is going to be different from this main one that you can see, which is the most unstable parcel trace. So then you have this cyan line, this blue trace in between the dew point line and the temperature line. And that is going to be the wet bulb temperature trace. And we talked about the wet bulb temperature back in, I believe, video 3B of this series. And the wet bulb temperature is really not super applicable for severe weather forecasting, more so for winter weather forecasting, precipitation type, etc. And again, the wet bulb temperature, just for a quick review, is the temperature that a parcel of air cools to via when water is evaporated out of it. So we talked about this in depth back in video 3B. If you want to check out the definition, the full description of the wet bulb temperature, go back and see that. But again, not super important for severe weather forecasting, but the SPC does highlight it here, and it's more useful in winter weather scenarios. Then you'll see this sort of dashed red line. It's actually quite close to the main solid red line, the temperature profile. It actually pretty much is the exact same as the temperature profile as you go higher up in the atmosphere. That is the virtual temperature profile. And we talked about the virtual temperature profile back in video 3B as well. And the virtual temperature is the temperature that a dry parcel of moist air has the same density as a parcel of dry air. And again, if you want to see the full description of that, go back to video 3B. I'll have the link down in the description below. But this dashed red line is the virtual temperature line. Now, SPC, the program that plots these soundings, NSharp or SharpPy, uses the virtual temperature correction to calculate instability metrics, such as CAPE. And it's not often going to be very much different from using the exact temperature profile, but I just wanted to make you aware that the virtual temperature profile is plotted on the SPC soundings here, and it's used to calculate these instability parameters. Again, it's not going to be that much different if you use the main temperature profile, but especially lower in the atmosphere where it's, by nature a lot more moist than it is up high in the atmosphere, the virtual temperature does separate just a little bit from the actual temperature profile, but it's not super important. So then we have our values here that are labeled on the side. We'll start over here. This is the effective inflow layer. And we talked about the effective inflow layer when we were discussing hodographs. And again, that's the layer within the atmosphere where parcels that are forced to ascend have meet a certain threshold for convective inhibition and CAPE, or buoyancy. So again, it's plotted on the hodograph here by these blue lines. And basically the effective inflow layer is calculated by the program taking a parcel at every single level of the atmosphere here and allowing it to rise. And if it has CAPE greater than 250 joules per kilogram and SIN less than 150 joules per kilogram, that parcel would be part of the effective inflow layer. And when you have a surface-based effective inflow layer, any storm in that environment will be drawing air in from that effective inflow layer. And if it's surface-based, you'll have likely surface-based storms. So it's plotted here both on the hodograph and by this purple sort of whisker here. And you can see the effective inflow layer storm relative helicity is plotted there as well. And it gives you the height of that effective inflow layer as well as the base of the effective inflow layer. So effective inflow layer is plotted there. Then we have this pink bar here, which is going to be the maximum lapse rate within the 2 to 6 kilometer layer. So again, it kind of points out the lapse rate is, of course, the rate of decrease of temperature with height. And this is going to be the maximum lapse rate within the 2 to 6 kilometer layer above ground level. So that helps us figure out often the elevated mixed layer, where that elevated mixed layer resides in the atmosphere. It shows you, a little bit of, how steep the lapse rates are aloft. If the higher the lapse rate, this maximum lapse rate is, perhaps the higher the large hail threat, given that you do have steep lapse rates and likely high instability there aloft, to loft those hailstones higher up into the storm updraft. But that is plotted as well. Don't use it a whole lot when I'm forecasting, but it is nice to know where that maximum lapse rate is, because it kind of does point out where the elevated mixed layer is, if there is an EML. So then we have our LCL, LFC, etc. here plotted in brown text here along the right side of the Skew-T. So first we start here with our mixed layer, or mean layer, lifted condensation level. And of course the LCL, again, you can go back to the previous videos to see the full description of what the LCL, LFC, etc. are. But again, the LFC is kind of that lowest theoretical cloud base. It's where the parcel first becomes saturated. So again, we go up from whichever parcel trace you're drawing, you go up from the dew point at that level, then you go up from the surface temperature at that level, and where those two meet, again, you go up from the surface along the dry adiabat, along the mixing ratio line from the dew point. Wherever those two meet is your lifted condensation level. And this is using the mixed layer parcel here. And again, we're going to talk about what mixed layer, surface-based, most unstable mean in the next video, but the LCL that's plotted here is the mixed layer lifted condensation level. Then we get up to the most unstable LFC, or level of free convection. And again, going back to what we talked about earlier in the series, the lifted condensation level is that level where the parcel first becomes buoyant, or the temperature of the parcel first becomes greater than the temperature of the environment. And again, this is using the most unstable parcel here. Then we go up here, the freezing level is plotted here in feet above ground level, denoted as FZL. Again, that's where the 0 degree isotherm, which is highlighted in blue here, as well as the negative 20 degree isotherm is highlighted in blue here on these SPC soundings. But again, the freezing level is where that 0 degree isotherm first intersects that temperature, the environmental temperature profile. And in this case, it's going to be 12,366 feet above ground level. So that's plotted there on the right. And we also have where the minus 20 degrees Celsius and minus 30 degrees Celsius levels are. Not super important. That's going to be where that 20 degrees Celsius isotherm and minus 30 degrees Celsius isotherm intersect with the environmental temperature profile. Not super important. Again, it kind of goes to what the freezing level shows. If the freezing level is lower, that means you have colder air aloft, and it's more likely for hailstones to remain up in the updraft and increasing the large hail threat. But again, I don't use these too much when I'm making a severe weather forecast, but you can if you're looking at the potential for large hail. Then we go up here, we have the most unstable equilibrium level. And again, that's where the parcel becomes not buoyant, or the parcel temperature becomes less than the environment. It's the point above the level of free convection, or the LCL, where the parcel becomes cooler than the environmental temperature. So that's going to be at this point, and again, this is using the most unstable parcel here. Then we go up here to the most unstable maximum parcel level. And we didn't talk about this earlier in the series because it's not super important here, but the max parcel level is the level at which there will not be any more vertical motion with that parcel. So you might be saying, well, that's what the equilibrium level is. Well, when you have a strong updraft, the momentum of that updraft is going to take it past the equilibrium level, because it's moving so fast upward that even though the parcel becomes cooler than the environment, it's still going to rise because it has so much momentum vertically. But that maximum parcel level is where that's going to for sure stop. So if you've ever seen a thunderstorm and you've seen a thunderstorm anvil, and you see an overshooting top, that little piece of cloud that kind of rises above the rest of the top level of that thunderstorm anvil, that's the overshooting top. It's going to go up, and it's going to extend past that equilibrium level and go up a little bit higher than that equilibrium level. Because the updraft is so strong, it's going to keep pushing that updraft above that equilibrium level, even though the environment is no longer buoyant at that level. But the maximum parcel level is where that vertical motion is going to stop. So that is what we have for our Skew-T. So let's move on here to the right side now. So on the right side of the Skew-T, we have our wind barbs. So this is going to show our wind profile, and again, that's going to be plotted here on our hodograph. But the wind barbs here kind of show you the distribution of winds vertically in the atmosphere, and as we know, a wind barb, the direction of the wind goes toward the origin, goes through the flags and the staffs toward the origin. So in this case here, this example I just drew, this would be a southwesterly wind. It's going from southwest to the northeast. If we take the wind here at, say, 300 millibars, it's going from the southwest to northeast as well. Down here at the surface, going from basically south to north. So that would be a southerly wind. So wind barbs, again, the flags are 50 knots. The full staff is going to be 10 knots. And the half staff is 5 knots. So for example, here at, let's say 500 millibars here, we have a 50, 60, 70, 80 knot wind. At the, let's say at this barb right here, we have a 50 plus a half barb, so that'd be a 55 knot wind. Just a refresher for you on wind barbs and what they mean. So again, that's the vertical distribution of the winds throughout the atmosphere here. And we can kind of see that in a different sort of visual here using this chart right here. This is going to be the wind speed in knots with height. So it basically takes all these wind barbs and plots them as sort of a vector. The magnitude is greater as the wind speed is greater. So this does not have anything to do with direction here. This is simply a plot of wind speed with height. So this would show you your speed shear with height. And you can see it's color-coded as well, and that's going to be for every 3-kilometer segment. And it corresponds nicely to the hodograph. You can see here on the hodograph, the lowest 3 kilometers is in red, and again, over here, they're plotted in red on this chart. The next 3 kilometers, the 3 to 6 kilometer layer, is in light green. That's given here. You can see the 3 to 6 kilometer layer is in light green, and so on and so forth as you go up in the atmosphere. Now, I really don't use this box at all when I'm forecasting severe weather. You can see, I think, more fruitfully what the winds are doing with height using the wind barbs over here as well as the hodograph. But this is here just to kind of show you the distribution of the wind speeds with height. So the next box we're going to talk about here is the inferred temperature advection box, which is right here next to that wind speed with height plot. So as we know, advection is the transport of a quantity, and this is going to be the temperature advection profile as you go up in the atmosphere. So as we've learned previously in this series, when you have clockwise turning winds with height in a layer, or veering winds with height, you have warm advection in that layer. In contrast, when you have backing winds with height, or winds that are turning counterclockwise with height, you have cold advection in that layer. So this temperature advection box gives us layers in which there is warm and cold advection based on the wind profile as you go up in the atmosphere. So you can see here in the first kind of 2 kilometers or so, you can see that we have warm advection here. The red boxes are going to be for warm advection. And you can see here on the hodograph that kind of makes sense. We have clockwise turning winds in the first couple kilometers in the atmosphere. But then the winds start to back a little bit, and you can see here that we have some cold advection going on just above that here. And then we have basically all veering of the winds with height in a general sense, and we have generally warm advection as we go up in the atmosphere, given by the rest of these red boxes here. Now the numbers are not super important. It kind of tries to quantify the amount of temperature advection ongoing within each of these layers. But the accuracy may be tainted a little bit because we're making some sort of assumptions, and I won't go into what those are. They're quite scientific, but the assumptions may make these numbers a little bit off, but it at least gives us a general picture of where there's cold and warm advection going on in the atmosphere. Now, I've never really used this box at all when I'm making a forecast. You can see where there's veering and where there's backing using the hodograph, I think in a much easier, much more clear fashion here. But this box is there just in case you wanted another visual to sort of see which layers have warm advection, which layers might have cold advection. So now we'll switch over to an example model sounding here, and you can see it looks pretty much exactly the same as the SPC sounding, except for maybe the color scheme here and there. but it's pretty much exactly the same because they're created using the same programs, with the exception of this portion on the left side of the Skew-T. And these are the omega bars. And omega, which is kind of written as this fancy looking W here, this is the Greek letter omega. It's a quantity in meteorology that represents vertical motion. So when you have, and this might be a little counterintuitive to you, but when you have negative omega, that means you have upward motion. And when you have positive omega, that means downward motion. So you might think, well, that's kind of weird, but it comes from the omega equation in meteorology, and I'm not going to get into that right now. That's beyond the scope of this video. But when you have negative omega, that means vertical motion. And it's just the way the equation is manipulated, the variables and terms are manipulated. It comes out that if you have negative omega, you have upward motion. If you have positive omega, you have downward sinking motion. So over here on the left is our omega bars. And when you have omega bars, when you have red bars here extending out of this portion of the sound of the Skew-T, the model sounding, and this is going to be only found on model soundings, it means that you have clicked a sounding, you've generated a sounding within an area of upward motion, i.e., you've generated a sounding in an area of convection or convective updraft, which is why we have negative omega here, and these red bars represent the upward motion. And blue bars, which I'll show you in a second, are indicative of sinking motion. So you'll notice here that we have these bounds here on the omega here, plus 10 to minus 10. And these are going to be the bounds of synoptic or large-scale vertical motion. And when the omega bars, when omega on a smaller scale here, on a convective scale, so these bars basically, when these bars exceed these bounds of synoptic scale vertical motion, the sounding pretty much becomes unusable. In other words, it's convectively contaminated. And you'll hear this a lot when you contaminated. You'll hear this a lot on Twitter, whatever, when people post soundings that have all these massive red bars coming out of this omega portion of the sounding. Well, that's because they've taken a sounding in an area of convection, and what that does is it really idealizes the profile. Here's an example of a convectively contaminated sounding. You'll notice how the profile here is very, very saturated throughout the entirety of it. Is that really representative of the background environment? No. Also, the hodographs tend to become very much enlarged because you're taking it in the middle of a storm, which is going to idealize the wind profile as well. So if you're looking at this sound, if you take this sounding and you would look at it just like this, you might think, well, this is a huge hodograph, over 1,000 effective inflow layer SRH. But you have to note these omega bars. Here we have a very strong convective signal, particularly in the low levels here, particularly in the mid level. So this has been taken in some area of convection that's ongoing on the model. Now these blue bars here are indicative of sinking motion, and in this particular case, I'm not quite sure why that is the case, and I'm not sure that sinking motion has too much of an effect on things if you see just a sounding with minor blue bars here, minor sinking motion here, minor omega. I've seen several severe weather events where you have these kind of weak kind of blue bars here on the omega scale, and you still get convection. So it might just be a model quirk there most of the time, but these red bars are definitely more important. When you see these red bars exceed that minus 10 threshold for synoptic scale vertical motion, you'll know the sounding's been convectively contaminated and it is unusable. So if you see soundings posted on Twitter or something where you have these long red bars extending out of here, you'll know that sounding is unusable because, again, the profile is too idealized and it is not representative of the background environment. So that's going to wrap it up for this video. I'm going to stop right here. I think if we did the whole top section today, we'd run a little bit long for this video. So I'm going to split up this kind of Skew-T portion of the hodograph, or excuse me, of the sounding, and the hodograph portion. I'm going to save the hodograph portion for next time. And then in the subsequent videos after that, we'll get into the bottom part of these soundings here and tell you all these different parameters and what they mean. So with that, thanks for watching. We will see you in the next video.